Welcome back. So the last time we looked at Taylor's theorem and we looked at its proof as well. We'll continue with Taylor's theorem and then move on to a different topic. All right. So there are a couple of questions unanswered about Taylor's theorem. Firstly, the Taylor polynomial, if you write down all the terms of it, it's called the Taylor series, as you may very well know. So here are a couple of questions about it. Firstly, when does the Taylor series converge? So what does it mean for a Taylor series to converge? What is a Taylor series? Well, f of a plus f dash a x minus a. This is in one variable, of course. We can talk about the multi-variable case as well. For now, let's stick to one variable. When does it converge? This question can be answered, but rather than giving you the complete answer of when it converges and so on, which will take us somewhat far away from our objective in this course, which is really multivariable calculus. Let me give you an example of when the Taylor series converges and when it does not converge, and what we really mean by convergence also. So for example, if you take this function 1 divided by 1 minus x, yeah. So if I want to write the Taylor series around the origin, suppose this is f of x, f of 0 is 1, f dash of 0 is also 1, and so on. F double dash is what? Please think about it. The point is, I claim the Taylor series is basically just this. Right. What does it mean for this to converge? Well, the simplest notion is the notion of pointwise convergence. Right? Recall that means the following: you fix the value of x and you look at this series, okay, as a series of numbers, right? Maybe from 0 to infinity if you prefer. We all know that if a series converges, if it converges, then the limit as n goes to infinity of an must be 0. So in particular, if mod x is larger than 1, surely the limit of x raised to n as n goes to infinity is not 0. In fact, it may not even exist, yeah, if x is negative, for example, but or it might be infinity if x is positive, but whatever it is, it's certainly not 0. So this does not converge pointwise, which is the simplest notion, if mod x is larger than 1. What if mod x is less than 1? Does it converge? Well, it does, and it converges to this original function itself. And this we know because if you truncate this after, let's say, n terms, this, we all know the formula for this, the famous geometric series formula, right? And as x goes to infinity, this goes to 1 as n goes to infinity. So in this case, it does converge and it converges to the original function. And when mod x is larger than 1, it doesn't converge at all. When mod x is equal to 1, that is when x is plus 1, this certainly doesn't converge. And the same is the case when x is minus 1 as well, okay? Does not converge. So this is not the prototypical example. Nonetheless, it tells you one example where the Taylor series can fail to converge, and it also gives you an example where the Taylor series does converge and converges to the original function, right? So the answer to this is not always. What about this one? This sounds like a very strange question, right? If the Taylor series converges, you would obviously expect it to converge to the original function. To what else can it converge, right? Here is a very interesting example, and this is not really relevant for the rest of this course, but if you want to, for example, pursue multivariable integral calculus, or if you want to take a course in differential geometry, for instance, and so on and so forth, it's useful. It's also useful if you're, for example, interested in certain aspects of condensed matter physics. For AI and ML, it's not particularly relevant, but it's still useful to know this example. Who knows when things can be useful, right? So this is also not always. And the example is not trivial at all. Yeah? Let me write this example. So the example is as follows. You take e raised to minus 1 by x square when x is positive and 0 when x is less than or equal to 0. What would its graph look like? So it's 0 and t raised to minus 1 by x square, it keeps increasing. As x goes to infinity, 1 divided by infinity goes to 0, so it approaches 1 eventually, right? The first claim is f is a smooth function on all of R. This is a very strange, a priori it must appear like a strange claim, right? It's a smooth function. What does smooth mean? All its derivatives exist and are continuous. And why is it strange? Because it's 0 all the way until x equals 0 and suddenly stops being 0. So notice f of 0 is 0, which is the same as, if this is the case, then f dash of 0 is 0, f double dash is 0, and so on. Why? Because they were 0 on this side, right? If you pretend that if you look at f from x less than or equal to 0 side, that is, if you write f dash 0, for example, as the limit as x goes to 0 from the left hand side of f dash of x, you would get 0, right? Likewise for f double dash 0 and so on. So if f is genuinely a smooth function, then indeed these are all 0, which means the Taylor series is, shockingly enough, identically 0. So not only does the Taylor series converge, it converges to a constant 0. And yet this function is not a constant. It is not 0, right? So this is a shocking example where the Taylor series converges manifestly and yet does not converge to the original function, right? So this is a very strange example. One fancy way of putting this, not really essential for the rest of this course, but it's this f of x is not real analytic. That's the fancy name. But don't worry about the name here. The point is the Taylor series converges, but it's not the original function itself. This, by the way, is a very surprising example. I mean, normally one would think that in the real world, right, we happily approximate functions by their linear approximation or by their Taylor series and so on. This is a very common practice in physics, for example. In fact, we were told as physics students that the opposite could never occur in nature, but surprisingly enough, a variant of this function, not exactly this one, plays a role in the real world. It's called the KT phase transition, if you want to look it up on Wikipedia. It's called the KT phase transition, and it's related to a Nobel Prize winning topic in physics. Yeah. So in other words, even this very strange function does occur in real life, okay, at least in physics. So the question is, how does one prove that f is a smooth function? Well, this is just a basic exercise in calculus nonetheless. Let's do it anyway. So obviously, if x is positive, f is smooth. Why? Because f is basically this, right? And 1 divided by x squared is smooth when x is positive. Rather, 1 divided by x squared is differentiable when x is positive. In fact, it is smooth. Rational functions are smooth wherever they're defined, right? We'll also give a proof of this fact in a moment. But the question, and if x is negative, of course f is smooth. No problem there because f is identically 0. The problem is, what about x equals 0? That's the real problem, right? So is f continuous at x equals 0, for example? Limit as x goes to 0 plus, for instance, e raised to minus 1 by x square is what? This is x goes to 0, so it's infinity, 1 by infinity, so x goes to 0, so this is 1 by, so it's e raised to minus infinity essentially, so this is 0. This is of course x goes to 0 minus f of x, because this is identically 0 anyway. So it is continuous, no doubt about that. Yeah? Right. What about, say, differentiability? Limit as h goes to 0, f of x plus h minus f of x divided by h, f of h divided by h. Again, so you have the left and right hand limit. I hope you're familiar with the fact that in one variable calculus, if you compute the left and right hand limits and if they're equal, then the limit exists, and if they're not equal, the limit doesn't exist. You can prove this, but nonetheless. So this is the limit of e raised to minus 1 by h squared divided by h, and this is identically 0 anyway, right? So how does one compute this limit? I mean, there are a variety of ways to do it. For example, you can use the L'Hopital rule, and you can conclude that this is 0. That's one way. Another way is to just do it from scratch. I mean, you can prove that, essentially exponentials decrease faster than polynomials, which is, in fact, it's a part of L'Hopital's rule again. Anyway, how would you prove that, right? So this is easy to prove using L'Hopital's rule, for instance, right? But you can clearly see that this becomes complicated for higher derivatives. So the real point here is there exists a polynomial of degree at most 3k such that the kth derivative of x exists is pk of 1 by x e raised to minus 1 by x squared when x is positive, and 0 when x is less than or equal to 0. Okay? So we can prove this claim by induction on k. Right. Okay, so for k equals 0, we know it's true. It's triviality. We've already seen this. Assume. the truth of this statement for k equals 0, 1, 2, 3, so on until k minus 1. What does this mean? This means that f is k minus 1 times differentiable even at the origin, and its derivative at the origin is 0, k minus 1 times. And more importantly, we know the k minus 1th derivative, it's equal to this. When x is positive and 0 when x is less than 0, right? Okay, so now we simply have to compute the kth derivative. So what is the kth derivative? So when x is positive, it's simply by the product rule, it's pk minus 1 dash times this plus the derivative of this, which is x cubed pk minus 1 when x is positive. Yeah? Now the point is, this is a polynomial, I'm sorry, this it's a polynomial pk of 1 by x, right? So I forgot about that, times minus 1 by x square. Okay? So what happens? So this is e raised to minus 1 by x square times pk of x 1 by x. This is of degree at most 3k. Indeed, this is a polynomial of degree 3k minus 3 at most. That times 1 by x cube would make it a polynomial of degree at most 3k, and this is an even smaller degree, right? So no problem there, right? Now fk of x is of course 0 when x is less than 0. So the question is, what about this? This is the limit as h goes to 0, fk minus 1 of h minus fk minus 0 divided by h. This is 0. Right. So again we have the left hand limit and the right hand limit. This one is 0. This one is also 0. Why is this so? You can use L'Hopital's rule, for example. When you use L'Hopital's rule, the derivative with respect to this becomes 1. The derivative of this with respect to h would become fk of h, and or it's in fact you don't even need to use L'Hopital's rule. It's just this is the definition of the derivative. The point here is, why is this limit as x goes to 0, 0? Because this can potentially run off to infinity, whereas this goes to 0. Okay, here you can, there are a number of ways to do this. I mean, exponentials decrease much faster than polynomials can increase, so that can be proven using L'Hopital's rule. But anyway, this is an elementary exercise in one variable calculus, so I'll leave this to you as an exercise. Yeah. Okay, so this is a very interesting function, as you can see, because of this strange property that the Taylor series is identically 0 and yet the function is not. Yeah. In fact, we can do something more interesting with the strange function, and we might as well do it. So the idea is, what's the graph of this function? If you look at the graph, it looks like this. Suppose we reflect it. What does this mean? This means that this new function is f of minus x. Right? So the values of when x is, here when x is less than 0 it was 0, here when x is larger than 0 it's 0. Now you translate it a bit, which means maybe let's give these things names. Let's say g2 of x is g1 of x let's say this is 1, for example. If you say this is x minus 1, for instance, maybe let's call it a more generally. When x is larger than a, then this argument is larger than or equal to 0. So g1 is 0 when the value of x is larger than or equal to 0. So this is correct. Now you multiply this with this. What will you get? You'll get something like this. Right? I mean, beyond a, it's 0. Over here, it's 0, and it's positive in between. This is basically f of x times g2 of x. This is a very interesting function. This is an example of a function with so-called compact support. I'll define what support is in a moment. So let me make the definition, but the point here is this function is 0 outside of a closed and bounded interval. It's 0 outside of a compact set and is yet smooth. So if you think about it, if I ask you naively, give me an example of a function which is 0 outside a compact set and is differentiable, right? For example, this is not valid because it's not differentiable. Well, what you can do is you can probably take something like this. This is like a cubic here, and you smoothen it out. So this is like a polynomial, and you cut it off here and declare this to be 0. The problem is over here and here, it's not smooth. So if you merely take a polynomial, you won't get a smooth function. So this is not a straightforward thing to construct, right? So this is an interesting example. So let me make a definition here. We won't use the definition, but it's useful to know the definition just in case. Let f from x to Rn be a continuous function where x is a metric space. Now, if you're not familiar with the metric space, we didn't really define a metric space in our detailed overview, but I assume you know it because it's a part of, say, any standard real analysis course. Nonetheless, if you're not thrilled about this notion, just pretend x is Rm for some m, okay? Doesn't matter. The point is the places, the closure of the set x where f of x is not 0 is called the support of f. So as the English word support, places which is supporting f in a sense, there are places where f is not 0, but you take the closure of it. So you get a closed set. In particular, outside the support, f is surely 0, right? So a function with compact support is one that is 0 outside of a compact set, okay? So if x is itself compact, for example, if you take a closed and bounded interval as x, right, then every continuous function on it has compact support, because regardless of where f vanishes, right, the set is itself compact, right? So the support, which is a closed set, any closed subset of a compact set is compact, right? Whenever you take any metric space, I mean in particular if you take 0, 1, for example, the closed interval, the 0, 1, any closed subset of it is compact, right? So every function is compactly supported there. So that's not saying much. When x is, on the other hand, not compact itself, for example, if x is all of Rn, then this definition makes more sense, okay? Right. By the way, we can we can take this same continuous function with compact support and play more games with it. It's what we can do. What did we call this? Let's call this G3 of x. Okay, let's give this a name. Right, so this is G3 of x. Here's a very interesting thing to do. You integrate G3 from minus infinity to x. Okay, maybe we'll call it G4. What does the graph of this beast look like? You're not picking up any integral. When x is here, for instance, the integral from here to here is 0. When x is here, the integral from here to here is 0, and so on. So G4 is still 0 here. When x is here, the integral from minus infinity to this point is the area until this point. Right? So the area keeps increasing. At some point you stop increasing the area because the integral from here to here is the same as the integral from here to here because you've already picked up all the area possible, right? So this becomes constant at 1, which is very different from the original function which asymptotically approached 1. This is exactly a constant. Now you play the same game, namely you just reflect, right? And then you translate. And then you multiply this and this, and lo and behold, you get something even stranger than before, in that not only is this function with compact support, it's identically 1 in this region, right? This is an example of what's called a bump function. Yeah? So it's identically 1 in some specified interval and it's 0 outside a compact interval. Okay. As I said, this is not directly relevant to what we will be doing later on, but nonetheless it's an interesting thing to keep in mind. As I said, if you ever want to do multivariable integral calculus, or for example if you want to do differential geometry or partial differential equations and so on and so forth, these sorts of things are extremely important. Yeah. This is not the only way of constructing these sorts of continuous functions with compact support or bump functions and so on. There is another construction too, but this is the most transparent one in some sense. Okay. Right. Okay. So now let's move on to a new topic, right? So returning back to differentiability, remember this function sine inverse of x, right? So the question is, suppose assuming sine inverse is differentiable, we know what its derivative is. Why? We know sine of sine inverse of x is x. So by the chain rule, cos of sine inverse of x times the derivative of sine inverse of x is 1. So the derivative of sine inverse of x is 1 by cos of sine inverse of x. And this is what, 1 by square root of 1 minus x square, provided, and obviously x belongs to the right domain and so on and so forth, right? So I mean, forget this. This is irrelevant. The bottom line here is we have a nice formula for the derivative of sine inverse of x, assuming it is differentiable. This is a very big assumption. In fact, we came up with a similar sort of a formula for more general functions. If f inverse is differentiable and f is a multivariable function, then f of f inverse of x is x. So the derivative of f at the point f inverse x times the derivative of f inverse at the point x is identity, which means the derivative of f inverse at the point x is the inverse of this matrix, right? The trouble, however, is this very strong assumption that F inverse is differentiable, right? I mean, in one variable calculus, if f of f inverse of x is x, so f dash of f inverse of x is, times f inverse of x dash is 1. So if f inverse is differentiable, for sure f dash is not 0, right? It's invertible, so it's not 0. Right. The question is, when will we know whether the inverse of a function is differentiable or not? Okay. So this we shall answer the next time, right? So we'll stop over here. Thank you for joining.